Okay, good morning everybody. Let's get started with the first lecture. This will be about laminar and turbulent flow characteristics. I'm quite sure that you came across that in fluid mechanics, but let's go through that quickly, at least to make a quick revision and just to make sure that we are all in the same page when we talk later for certain vocabulary in this course. I think all of you know what is really meant by laminar and turbulent flow. This is the key objective of this lecture, and we will come across, as you came across in the fluid mechanics course, about how to tell that this is a laminar or this is a turbulent. You all know Reynolds number, and Reynolds number is the number or the term by which we can tell whether we have a laminar flow or a turbulent flow. And in this case, we are talking about a characteristic for the flow. I mean, we have to distinguish between flow type and flow characteristics. Flow type, when we say, for example, steady, or when we say uniform. What is meant, by the way, by uniform flow? Can anybody answer? Yes, please.
No change with place or location.
With distance. So I would assume that the velocity will not really change from location to location. This is uniform flow. And when we say unsteady or steady or transient, what does that mean? Yeah, there's no change with time, then that would be a steady flow. Now we are talking about characteristics. That means the flow might be laminar, yet it could be steady or uniform, or it could be unsteady and non-uniform. So we have to distinguish that. Just really without going through the slides, because I'm quite sure you know them, and there's no point to duplicate the effort here. But what is meant by laminar? When we say that the flow is laminar, what feature the flow will have when it is laminar, please?
Reynolds number less than 2100.
Yeah, 2100 or 2100, yeah? Or you can find sometimes 2000, sometimes 2300, something in that region. If the Reynolds number is less than that number, that amount, then it is laminar. But I'm not talking from a quantitative point of view. I'm talking about from a descriptive point of view.
Mainly, the flow is mainly affected by viscosity.
Yes. So the impact of viscosity on the flow is major. And it exceeds the impact of what?
Of friction.
No, it's friction. Viscosity is friction. Yeah, this is fine, but let's see. Let's write. Hold on. Reynolds. I think this will take forever to write something here. Equals rho. Okay, now this is Reynolds number, the density of water, V is, or the average velocity, let's say it like that, the diameter, dynamic viscosity. Now there are two types of viscosities, or we can say kinematic viscosity, something like that. Anyhow, so this represents the viscous effects, but this represents the inertial effects. I mean the ability of the fluid to resist any force that is trying to keep him unflowing or non-flowing or whatever. So if Reynolds number is less than 2100, then this is laminar. That means the viscosity will suppress the flow and the flow will travel in a slow velocity. But if it is really larger than 2300 or something like that, then that will be a different value in the end. Now, this is one thing. The other thing is what other characteristic for the laminar flow. Now we talked about that viscosity is predominant. What else? it goes in an order way. That means in a kind of layers, layer above layer above layer, but not really in a random way. There's no mixing. There's no randomness. I mean, if we look at the slide, and I think you came across something similar to that. When you open the faucet is the tap. This is the faucet. If it is really, it gives low flow, then the flow has a low velocity and it will be laminar. But when you increase the flow rate, you will start to see randomness and start to hear the sound of water because of the mixing that is taking place. So with laminar there is flow, there is no mixing. With turbulent there is mixing between the water particles. If you look at this, can anybody describe this? What is this? Did you see this before, by the way? Yeah, what does that mean? How can you describe this? This is a pipe and this is the flow, but the flow is kind of concentric. Do anybody know what is meant by concentric? It's like circles in circles in circles. So this is like layer of flow, layer, 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 and there is the inter-viscous impacts between the different layers. This is the what you did take the viscosity impact on the flow itself. Now, if this flow is uniform, and this is laminar, by the way, because it goes layers as layers, but the layers are circular because the flow is going through or flowing through a pipe. If it is going through a flat surface like this, then it's like sheets. Simple as that. Now, if the flow is uniform, so the flow rate will be constant. That means if I consider this as a small pipe, then the flow rate is the same as the flow rate here, is the same as the flow rate here, is the same as the flow rate here. Now, if you recall the continuity equation that you did take in the fluid mechanics course, Q equals the continuity equation, V A. Now, here, where is A? Now, I can take this small size, volume, or control volume, and the cross-sectional area is the smallest, but the velocity the largest. And if I take this one, this is the largest area, because you have to take all the way, but with the smallest velocity. So, you need to keep that in mind. This is very important. I think this is the major idea from putting this figure here. Two things, that the laminar flow is like a sheet flow, layer flow, and the second thing which is more important, that we have a velocity distribution. Yes, we can describe the velocity as an average velocity, an overall value for the entire pipe. And by the way, in hydraulics we deal majorly with average velocity, but in this chapter they distinguish the velocity at the center line being the maximum velocity, and the velocity at the boundary itself being the minimum and equals 0. And thus we have a velocity distribution that we will come later on across. Now, when you increase the flow rate from the faucet, the tap, then you will start to witness randomness. As you can see, it's quite apparent. This is kind of transitional, by the way, because if you compare that with this is sharp, no edges, fluctuation at the sides. But when you look at this is more or less random effect, and this is turbulent. And this again high velocity, characterized by high velocity, and the inertial forces will dominate over the viscosity effects. I think this is just a repetition of what we already said. Did you come across this as well? Now, I can just explain it quickly. Imagine that we have this reservoir, the flow that will get started because of opening the valve here will get its potential from this elevation of water here. Now, if you add a dye, what does it mean dye? زي صبغة. If you add a dye at this location, if the flow rate is very small, what do you expect for the dye that will leave out? It will be like a line. Like that. But if you increase the flow rate, then what will happen? Mixing, and we will get randomness. So this is the situation. This is kind of laminar flow. You see, this remains on the same path, this remains on the same path, and the dye will not get mixed. This is laminar flow. But if we look at this one, now because we have increased the flow rate by increasing the opening of the valve, then mixing will start. It's exactly like these balls that we have here. These are numbered, and if this is laminar, then the first one, you have to imagine that this is one ball, but after some time is the same track, the same path, the same way. But here 2 became down, 12 goes up because of the mixing. So everything will get mixed up when we have transient conditions. This is again, I think now this is repetition. This is laminar, this is turbulent.
So
Yeah.
بين اللامينار والتربلنت مش في ترانزيشن؟
Yes.
كيف بدنا نحدد كل منطق كل وحدة؟
Yeah. Now we will come across that. There is Reynolds number limits, and from that we can tell. But this again, this is kind of laminar, and in part this is transitional, and then you can say the other one is turbulent. I think this is already, we said that. This is the guy who invented or brought up the Reynolds number. Now, this is, you have already taken that. I don't really want to duplicate things. You need just to memorize that one. Now, as I already said, and one of your colleagues said, if it is really less than 2,300, in some textbook you can find it 2,000, other textbook you can find 2,100. But if it is really less than that, this is laminar. If it is really up to from 2,300 up to 4,000, then this is transitional. And if it is really greater than 4,000, then this is turbulent. Now, two things. The first thing, in reality, this is what I really care about now. Do we have laminar or turbulent flow? Turbulent. Why? Yes, this is right. Now let's write this again. Okay. Yes. Why? Yes, why? I mean, what will make this high? Two things, mainly.
The main velocity.
Assuming that diameter is not changing, velocity could be high, or viscosity is low. Now, for water, we are talking about water. What would be the dynamic viscosity of water? You came across it in fluid mechanics. How much? No. العكس. Yeah? Yeah. Instead of saying this, yeah, minus. Units. Okay, or yeah, as you said, this is Pascal. I don't like it, but we can say I like this more. Anyhow. But also you can even if you don't really need to memorize that, because you can say this is dimensionless, then mu equals rho kilogram per cubic meter multiplied by meter per second multiplied by meter. Then you can tell what would be the units of that one. Now, back to my question. In reality, now this is 10 to minus 3. The velocity, what would be a reasonable velocity in reality for water in a piped?
1 meter per second.
Okay, the maximum value could be, one is for design purposes, but it might go up to 3 meter per second. For the diameter, what would be a reasonable? 1 inch is less than the lowest. It should not really fall below 2 inches. So, rho 1000 multiplied by V2 okay, multiplied by 2 inches. The inch is 0.0254. That will take forever. I think we can do it. Again, 1000. This is the density of water multiplied by 2 multiplied by the 2 inches to
5.8.
this is in meters because each 1 inch is 0.0254 divided by, so at least this is how much? Million. And as much as you are putting this down, it's still larger than 4,000 for sure. And we are talking here about something greater than 100,000, something like that. So we are talking about something greater than 4,000. So just keep in mind that in reality, this is the case. Okay. There are really some examples here. There's no point really to go through because you already did take that. But at least you might find Reynolds number written in this way. This should not really confuse you. The velocity is given for you, the diameter of the pipe, the density of the fluid, the viscosity is also given for you as well, and you can calculate Reynolds number. Generally, Reynolds number, you need that to be able to characterize the characteristics of the flow, and then based on that, then you can decide of what kind of equations you are going to use further later on, as we are going to see in the end. I think this is fine. We can skip all of that. We can look at this at home. What else? Okay. There might be a different way of thinking of Reynolds number. Like, for example, let's read that question. Water has a kinematic viscosity of 1.139 multiplied by 10 to minus 6 square meter per second and flows in a cylindrical pipe, okay, circular pipe of 30 millimeter diameter. Calculate the largest flow rate for which laminar flow can be expected. If we get back to, we know that again. The velocity equals Reynolds number like this, and equal that. Then we can just say Q over A. And then we can say as well for Q like this, and you have everything. You have the diameter is given for you, you have the dynamic viscosity, you have the density, and you have the diameter as we already said. Reynolds number, yeah, now it says for which laminar flow can be expected. The maximum Reynolds number for laminar flow to take place either 2000, 2100 or 2300, something like that. So just you plug in the value, for example, whatever, you are free to use which value you want, and then you can find the Q value. If the flow rate increases above this value, then the flow will become transitional. And if it increases above a value that will make Reynolds number 4000 and beyond, then it will be turbulent flow, things like that. So the idea here, Reynolds number will help us later on to verify. Verify means to help us in selecting the right equation to use, because when we come later on for example evaluating the head loss, there are three types or three situations, and this is very important to keep in mind. There is general, and there is laminar, and there is turbulent. The general, as you did take in fluid mechanics, they call it fundamental equations. I don't want to really write word fundamental because it's really a large word, no enough space for that. So fundamental equation, like what a fundamental equation could be. Can anybody?
FL على DT squared.
Yeah, this is a fundamental equation. The head loss what is meant by fundamental equation?
Can be applied to any type of.
Exactly. Any type of flow can this equation be applied to describe it in terms of head loss, or if we know the head loss, to know what would be the average velocity, and so on. Q equals V multiplied by A. This is a general equation, fundamental equation. Then another fundamental equation that you come across, the head loss equal tau over did you take that equation? Yes? Okay. Let me see if there's anything left, by the way, then we can get back to that. I think this is maybe the last one. Yeah, let's get back for this. Okay. Now back to the equation that I already did write. The head loss this one. You already did take that one in fluid mechanics. Yes? Yeah, you saw that. And you saw this equation as well. It might be, as we said last time, it could be HL or HF. Don't really get confused. And we have now these two equations you have to memorize. المفروض تحفظوهم يعني. Especially this one. And you need also to memorize this one. Let's really look at the terms that are in these two equations. If we look at this equation, what it says, the head loss in a pipe or a conduit or whatever channel is related to the shear stress at the boundary, the length of the pipe, or not necessarily the length of the pipe. It's the distance that the fluid will, for example, move, migrate, reach, whatever, over divided by specific weight, وزن النوعي, divided by. Now this is important to know. What is this?
Length over diameter.
No. Hydraulic
Radius.
radius. Yeah? Not the radius, the hydraulic radius. And the hydraulic radius equals what? Yeah, the cross-sectional area of flow over P. But what is P? Sometimes they call it WP, wetted perimeter. Okay, not like, for example, if we say this is a pipe, this is a pipe, circular pipe, and it is fully full of water, completely. So the area, what is the area of the flow? It's an area of flow, not area of the pipe. Like, for example, if the pipe is like this, and the flow, the level of the water in the pipe is like this, then this is the area. Then we are talking about the area of the cross-sectional, or the cross-sectional area of the flow. This would be, we are talking about this case, not this case. And the wetted perimeter, what's meant by wetted? مبلل. So every edge here this is, so the length of that red line, and it would be 2 pi r or pi d. I prefer pi d. Then would equal like that. Yes.
السطح المبلل.
Yeah. مش السطح المبلل، المحيط المبلل. perimeter هو المحيط.
يعني بالحالة الفوقانية أول وحدة.
لا. We are talking about this case.
بعرف بس لو كانت بالحالة الفوقانية.
Yeah, there are equations for that, because in this case we will take that in open channel, but quickly you will assume this, there will be the center line, then you connect like that, and there is this one and this theta, then you relate everything according to that one. But for now, let's take the easier case, and there are equations that will describe that. But this is more important than this. Where we can see this situation, by the way.
Open channel.
No, but this is not open channel. This is closed. Yeah, this is wastewater collection network. So this is more important than this is water distribution, pressurized, non-pressurized, gravity flow, pressurized flow, and so on. So this is very important to keep in mind. I think even you need to memorize it. يعني بسهل عليكم later on, it will make your life easier when you come across situations like this. Instead of writing this and that and then divide, then you have that already ready for you. So this is the hydraulic radius. From this equation, for example, we can make a variation. Head loss over L. So just take that down, would equal what does that represent?
Slope.
The slope. No. Okay, no. Let's do it like that. Slope is right. How can we know that this is slope? I mean, why we said this is slope? It's correct, but why? Dimensionless. This is one. What else? What does it mean, a slope? In reality, slope of a street. What does it mean?
Vertical over horizontal.
Yeah, delta. change of something, pair change of something else. So delta pair delta. But what delta? Is this delta HL? Yes, absolutely. It's a drop in head. So this is delta H. Just quickly recall, H1 equals H2 plus head loss. So head loss would equal H1 minus H2. Simple as that. And L, simply, if this is a pipe, then this is L. But if we take coordinates, then this is X equals 0, as somebody said already, and this is X equal L. And then this is dH over dx, or delta H delta X. So this is slope. But slope of what? Somebody said wrongly, this is the slope of the pipe. This is wrong.
total energy line.
This is the total energy line. The slope of TEL. Can I say, for this case, it is as well slope of Can I say that?
No.
In this case.
The vibe is uniform.
Okay, let's get back. Delta H equals H1 minus H2. I'm talking just about this one now. Delta H equals H1 minus H2. The starting point and the ending point potential. And this would equal P1 over gamma minus plus Z1 plus V1 square over 2G minus like that. Now in this case, now this is total head at the starting point, this is the total head at the ending point. But if this is a pipe with constant diameter and not a varying flow, how can the flow rate vary in this pipe?
Diameter change.
No. Well, flow is flow. You can make the flow in 1 inch or in 10 inches. Like you have 10 people, they can enter through this door or 2 doors. Doesn't really matter.
في flow ثاني بيكون داخل.
I mean, Q is Q, but the velocity might change. This is what the point. But we are talking about Q. Now, the Q only can change in this case if there is another pipe connected. So part of the flow is being lost, but this is not really the case. So what kind of flow do we have here?
Constant.
Uniform. We have to use the word uniform. So in the case of uniform flow, then this V1 would equal V2. So it's correct. Yeah. But we need to keep in mind that in general we are talking about total heads, including the velocity head. So this is in general the right, but in our case, if we have a pipe doing like this, no, it's a different story. And we have to consider both situations in the end, because in this case, part of the kinematic energy were lost for increase in the, for example, pressure and so on. Now, so this is slope of the total energy line. What is the units of that?
Dimensions.
Yeah, but there's still units.
Meter.
Yeah, it's meter per meter. But they are different meters. This is meter distance, but this is meter energy, head. Yeah. So now if we get back to this equation, There's a term that you already did take in fluid mechanics, which is SF. So this is the friction slope or frictional slope. That means now our equation would become SF equals or the boundary shear stress would equal like that. Okay, so this is an important equation, but at least you can get it from this equation, the way that we already got that. Then you can as well make things also that then tau 0 equals gamma is rho g. This is if we are talking about circular,
D over.
then d over. Not only circular, also full flow. Please keep that in mind, because after we finish the pipe flow, we will not really get back to that. All our work will be in partial flow conditions, again, which is more important from a practical point of view than the pressurized situations. What else can we say? Now, if we get back to and then write them again, we have, as we said, SF equals gamma, and we have again HLF. Oh, sorry. Okay, now we'll do it. Okay. Like that. Now, what else? Can I make SF from this equation? I take this down, then it will become HL and then there a potential of equating this equation with this equation. And for example, you can say tau 0 equals gamma. Instead of SF, you can say F over D like that. And then you have now a relationship that relates here. This is a relationship that relates the boundary, again T0, boundary shear stress with gamma, the hydraulic radius, and the slope of the hydraulic grade line or the total energy line. But here, this is a relationship that relates on top of that the boundary shear stress with the average velocity. I think this is another new equation that you would like, that you might keep in mind. Now, if we look at, for example, instead of having a circular cross section, we might have a conduit like that. Now, if I close it like this, it's no longer a channel. And if I close it like this, I am assuming in this chapter this is pressurized flow. That means this is the level of the flow. Now, if I say, for example, this is 8 meter in width, and this is, for example, 6 meter in depth, then R H would equal the area of the flow, again, the area of the flow, 6 by 8, now we have I will do this for the last time like this. Everything in blue is the weighted per meter. That means absolutely. We'll do it this like this only this time. And then you can get that. If this is open channel, then let's draw it in the front. If this is now, this is conduit. This is like a pressurized pipe. But if this is an open channel, it will be, how many edges do we have? 3. Same dimensions. Water is 6 meters. Now the cross-sectional area of the flow will not really change. Yeah, this is. So A would equal 8 by 6. But the weighted per meter, only we have 8. But okay, I made a mistake here. It should not. Sorry, it's like that. So it's 8, the bottom and the sides. Okay, so this would be the hydraulic radius. These are very important. I mean, to me, to understand that is quite essential. The last thing that good now to mention, and then try to finish this chapter, God willing, next Thursday. Let's just get back to Darcy-Weisbach equation. Now, this equation in this form applicable to what kind of cross sections in this form? Circular. Why? Yes, right. Diameter. But how can you really use it for non-circular pipes? For example, I gave you a pipe, a conduit like this. How do you really use that equation for that case?
نضرب بمساحة الدائرة طرفين وبعدين نضربها بعدين نضربها من الناحية الثانية مساحة cross section لها.
Okay. Now, if we think more, now the hydraulic radius for a circular pipe, what equals? Yeah, we already said that. So the diameter equals. So we go and we just take that. And we can say over 4 RH. Now you can tell what is RH here easily. So this is the way to be able to use this equation for non-circular pipe. So here, for example, this is B. Generally they consider that B. And this is, you can say H, but the common is Y. Name it this way. So RH, assuming that the flow is just pressurized, then it will be By over 2B plus 2Y. And just you will have number, just you calculate RH, then you go and plug it here, and then you do the calculation in the end. Next lecture, I will get back to 7.2